Okay, so let's get started with the afternoon session. So we are very happy to have Yuan Miao from here, local speaker, who's going to tell us about the Floquet Baxterisation. Please, Yuan.
Okay, thank you very much. And first of all, I'd like to thank the organizers, especially Filippo, for putting up this very fantastic workshop. Also, it's my first time to give a talk in person at GGI, so feel privileged. So today I'm going to talk about something called the Floquet Baxterisation, maybe it might be a bit, sounds a bit unfamiliar to many of you, but I'll try to explain at least some of the concepts behind all these two main topics. So to begin with, I would like to say that why we are interested in studying this problem. So first of all is that there's a very interesting problem studying the dynamics of quantum many-body systems. And because of the interaction, so this problem is actually quite difficult, especially for the cases out of equilibrium. So there are many recent works that have been devoted to this topic. For example, you can study the so-called quantum quench, or you can even think of a quantum many-body system that you drive it periodically. So this is so-called the Floquet dynamics that will be related to the main topic that I will talk about. And moreover, if you want to realize this system in a real experiment, usually people do is to study a quantum simulation of a quantum many-body system. And many ways you need to discretize both space and time. So this is so-called discretization of some quantum, let's say, quantum time evolution, such as quantum circuits or quantum cellular automaton. And this is very nice, but in order to really to study it thoroughly, you need to understand the full spectrum of the quantum many-body systems, not only just the ground state or the low-lying excited states. So you need to understand also the highly excited states. And in order to do that, maybe we can use something that we are familiar with, such as the integrability. But here I would like to present somehow a way to construct a discrete, both in space and time, integrable system using something that we know already, so namely from the statistical mechanics, the vertex model. So from the integrable vertex model, with some modification, we can actually use it to study some quantum system with both discrete space and time. So for today's talk, I will mainly start with something very slowly, because I presume that many of you do not know what is Floquet dynamics in quantum many-body systems. So I'll start to introduce what do I mean by Floquet dynamics, and then I'll talk about some essential ingredients that I need to study this, namely the Yang-Baxter integrability. And then, in order to satisfy many of the mathematicians who are sitting here, I'll present a proof. So of a theorem that I discovered with my collaborators, Vladimir Gritsev and Denis Kulov. And then I will also present some example in terms of six vertex model, which we discover some kind of anti-unitary symmetry breaking in the easy plane regime. Okay. Okay, so let's start with the first part. So let's consider a quantum many-body system with a time-dependent Hamiltonian. So I'm considering quantum Hamiltonian that Hamiltonian changes with time. But now I'm considering a very special one that is periodic in time. Okay, so the period I call it 2T0. Well, this 2 just for my own convenience, so it's not very important. And once you have done that, well, you might be interested in, let's say, the quantum system after each period. So maybe you want to study the time evolution operator, which I call it UF. So F stands for the Floquet here, which is some path ordered integral of the exponential of the Hamiltonian. And this is kind of, we are not really, let's say, monitoring the system at each time, but we are monitoring it in stroboscopically. Yeah, and this I can define the Floquet Hamiltonian. And here you immediately see that this Floquet Hamiltonian is not uniquely, because well, if you add, let's say, any integer of 2 pi over t naught, then yeah, then you see that basically your Floquet time evolution operator, which is physical, remains the same. However, this is I mean, so this is very similar to in the analog of having a lattice in real space, where your momentum will become also quantized into quasi-momentum, and here your energy becomes so-called quasi-energy. And here this I call it Floquet Hamiltonian, which in principle is not really local, because you're taking a logarithm with some operator, which might have a nice local property, but after it might, in principle, it is non-local. But let's consider an even simpler example. So let's consider a nearest Hamiltonian that contains only nearest neighbor terms. In this case, well, let's write down something called H naught, which is sum over L many terms. Let's see, we are interested in the Hilbert space of Cn tensored L times. And this local term of the Hamiltonian acts only on m and m plus 1 side. And in this case, well, you can decompose your H naught into 2 parts. So here I assume, let's see, the system size is boundary, just for simplicity. So I will call this part, let's say, H1. So let's say generically, if you consider, let's say, the nearest neighbor local density of the Hamiltonian, they might not commute. So if H1 and H2, they do not commute. And let's consider this scenario. Otherwise, the time dynamics will be trivial. But however, you can see that immediately among all the terms within H1, they commute because they have different support in the Hilbert space as well as H2. And let's consider some kind of some time-dependent Hamiltonian that are periodic in a very simple way. So let's say this H is H1, H2. So this is when 0 between T and T naught. Okay, let's put it this way. And here is between T naught and 2T naught. And also H of T is periodic in time. So I'm considering kind of this time-dependent Hamiltonian. So per definition, it is it's a Floquet system. And we can write down basically that the Floquet time evolution operator in a very simple manner, namely just the exponential of H2 T naught with the exponential of minus I H1 T naught. Okay, and this is essentially defined as exponential of exponential of, yeah. they do not commute. Because here let's say I consider the case where so this is just because I consider this a step-like protocol. So so in a sense you can in a sense we can consider something like this. So let's say this is like H1, then jump into H2. Some protocol like this. So in this case you can write your ordered exponential in this form. Okay. And this, basically, if you're familiar with, let's say, quantum antibody system, you will immediately realize that if you take the limit when T naught goes to 0, so what I'm talking about is limit when T naught goes to 0, and then you also involve this Floquet time evolution operator to 1 over T naught many times, and this will just be the trotterization of your original Hamiltonian H naught. So this is typically this is basically from the normal theory of, like, for example, if you want to simulate your time evolution from this H naught, you can do this trotterization scheme. But however, the question is, well, if we start with some integrable Hamiltonian H naught, under vortex cumulus, this UF would also be integrable. Namely, I would be able to find some transfer matrix that commute with UF, which means UF would have infinite many charges by taking the logarithm derivative of the transfer matrix. And in principle, I mean, maybe I'm interested in the regime where T naught is of order 1. So the period is not really infinitesimal, but of some order 1. And actually, I will present to you how to construct such, I would call it integrable Floquet dynamics, where the basic scheme is to make this UF to be some kind of transfer matrix by adding some spectral parameter, such that this UF will become a special point of this transfer matrix. And this scheme is, in spirit, very similar to what Jones did for so-called Baxterisation. But before doing that, let me just to set the record straight to introduce to you what is the integrability that I'm talking about. So, so the integrability that I mean is essentially the Yuan-Baxter integrability. And in this case, I'm considering some object called the R matrix. That really, in the, let's say, the endomorphism of two of this Hilbert space. Okay, let's be simplistic. Let's say n is some integer that's, let's not consider infinite dimensional. And now I write down the definition for, so the Yuan-Baxter equation that this R matrix satisfies. So here I would like to make a remark such that this R matrix that I write down, I do not assume, let's see here, let's see this remark. First is it's not necessarily of difference form. So what I mean by that is that sometimes your R matrix is really just the difference between the two spectral parameters, where this U and V, UVW are just some complex number, but I do not require this. So this is not important in my derivation. And secondly, usually people consider this R matrix to have this nice property called regularity, namely R matrix at certain, at certain point. I mean, you can rescale it anyway. So let's say 0, 0 is proportional to the permutation operator. But this I also don't need. You will see that, well, basically all the known examples of such integrable Floquet dynamics usually satisfy these two conditions. But here I do not assume them, so my proof would be a little bit more general than the existing ones. And also for my own convenience, I also define some object called R-check matrix. And R-check is defined as just R matrix multiplied with the permutation operator. Okay, where permutation operator, just to be sure, let's say it will change some operator from A to B. Okay, so at this stage, well, it's really just some ad hoc, let's say, definition, because I don't assume any regularity transformation. It seems maybe a bit useless to define this, but this object would be very important later. And using this definition, we can also get the Yang-Baxter equation for R-check. Okay, which I'll just do it here. Maybe here is be. So this is more. This will look more like a breeding. But in the end, I'm mainly using the previous one. Okay, so with this defined, so in principle, I could construct a transfer matrix that commute. But for my own purpose, I would define something called a staggered transfer matrix. Basically, so the staggered transfer matrix depends on U, some parameter, just per definition. So it's a trace over a monodromy matrix, where this monodromy matrix, so over the auxiliary space, and the monodromy matrix is defined just as a product of matrix. So I'm kind of bipartite my length, since I'm considering, again, even number of sites. Also, I consider the same here. So basically, from this Yang-Baxter equation, I can find an intertwiner that intertwines between these two. Okay, I'll omit these two indices. Okay, I will not, because just to not to be. Here it should be V. Hope it's visible. So this R matrix will intertwine these two monodromy matrix. With the same kind of. And what it implies, obviously, is that this transfer matrix, that kind of staggered transfer matrix, because I'm staggering between even and odd side, it commutes with itself with different spectral parameter u. So, and this will be actually the Baxterized Floquet time evolution operators. Okay, so this is so this is the main object that I will try to use. Okay, or if you want, you can also draw a diagram which will just exemplify what's happening. So you have odd side, and let's say this spectral parameter is u, this is v, and here you have some kind of, in a sense, inhomogeneity. And this is the R matrix that I wrote here. So this R matrix will intertwine them. So this is on the left-hand side, and this will equal to the other one with the same inhomogeneity, but with the opposite spectral parameters. So here is v, here is u. So this is basically to see this intertwining relation. Okay, it is v, but I have to apologize for my handwriting. Yeah, but however, if you choose different u0 or r, they will not commute, obviously, because there exists no intertwiner. And this actually is quite okay. Now let me present the theorem that I want to prove. Now, the third part. Oops. So this is a Floquet Baxterisation, a proof. Okay, let's start with the theorem, which I define some object called UF of U0 and alpha, which is product of all the. So again, I assume that I have even number of local degrees of freedom. Is it visible? I hope so. Maybe I can change chalk. So it's product of R check. Sorry, this is wrong. So essentially, it's very similar to the one that I wrote here, because if you think of this this UF, since all the local terms they commute, so this UF is essentially a product of exponential of all the okay, in this case is the other way around. Okay, all the odd terms and the product of all the even terms. Sorry, I said the wrong thing. Okay, so here is like first product of odd term and then even term. Here is the other way around, but it's up to us how to determine. And this is a very similar structure as I presented. And the theorem says that this object with this transfer matrix that I defined there, for any spectral parameter, complex spectral parameter. And the reason why I call it Baxterisation is that if you look at this UF, in principle, well, it contains one less spectral parameter than here. And basically, this T you can think of as you're doing the procedure of adding an additional spectral parameter. So this is philosophically very similar to what Jones called Baxterisation, even though the technical details are slightly bit different. But so I would like to prove this statement. Yeah. So this I will not erase for now, but this will be something I want to prove. And just before I do that, actually, you can think of this evolution operator as some kind of quantum circuits, because you see that your operator R check, it acts on only, it does not have any auxiliary space at the moment, and it acts on two sides. So you can think of this as just some kind of quantum circuits. That looks like this. So where for each box, it has to be the same operator. You see that you cannot choose the operator here, and I'm considering periodic boundary condition. So this is typically what this UF would look like. And basically, yeah, so basically now I want to prove that this UF commute with this transfer matrix. Also, I would define, let's say, UF as V multiplied by W, where basically this V here is just the product of all the, let's say, odd terms, starting with odd. And then this W here is a product of all the even ones. So basically, in my proof, actually, I will use some trick that I learned from Fadiev's lecture notes in Lazouche, I think back in 1996, maybe. Which is very similar to the way how you can find the local, to construct local conserved charges from the logarithmic derivative of the transfer matrix. And the way how to do that is first, since we have periodic boundary condition, so here is the proof. We realize that basically W, okay, let's omit the parameter here just to be a bit simpler, is essentially V, but translated by one side, because you see that if you translate 2m minus 1 to 2m, then you basically construct W, where this G is so-called the translation operator, is a product of your permutation operator, as I showed before. So if you move all the operator to one side to the right, then you basically construct, or to the left, either way, because periodic, you can transform V to W. And now I define some operator called O. So O is defined as basically V multiplied by G inverse. So if we write it explicitly, well, we have product of all the R check that acting on 2m minus 1, 2m, and then product of, okay, now I'm doing, because the inverse is simply just the product with the side, because permutation twice it's just identity. Let's say L minus 1 to 1. Also, it's very easy to see that PAB is the same as PBA. So that is why this is true. So this is G inverse, which is translation to the left. And here comes this identity that I learned from Fadiev's book, which is simply that this is a trace over some auxiliary, like let's say this is called OB, where OB is basically a product of the permutation. Sorry, it's not. So B is the like kind of some auxiliary space that I add to it. So because here it's only an operator acting on real space, but now I want to find another operator that acts on the another auxiliary space, such that I can use basically the intertwining relation of the R matrix. So here we have P of here of 2m minus 1 with R 2m. So I omit the spectral parameter, but here you can imagine this is U naught and alpha. So how to prove this is actually quite simple. It's just you just drag all the. So first you rewrite your R matrix using the definition for R check written here, and then you just drag all the permutation to one side, and this basically gives you this G inverse here. I wrote here, and then in the meantime, basically you realize that all your dependence on the auxiliary space will vanish except for one term, which taking the trace of that term just becomes 1. So this is something I learned from Fadiev's lecture notes, and then the remaining part is simple. So now since we have this transfer matrix which is trace over the monodromy, the question is whether we can find some kind of R matrix that intertwine between let's say this object and this OB. So if we can manage to do that, then basically we can prove that we can prove this theorem. And actually it's quite simple to see that basically if you have the monodromy defined as in here, this R matrix here is very simple, just U naught, and the reason is because if you look at the even side, so basically this is, let's say, we can use a different color maybe. So on this side, we basically have something like R A 2m minus 1 U naught, and on this side we have basically the permutation PB 2m minus 1. And this is actually because you see that this R matrix has the same spectral parameter as this one. So it's easy to just to drag this permutation to the other side, and it intertwines. So this is the same as this P, so R A 2m minus 1, R A B. And in the meantime, the other one we have for the even side we have the same here. And we have basically here is B 2m of U naught alpha. Sorry, here should be alpha. then you see that this is essentially the intertwining relation that I wrote before. So this is true where this R here is simply just this RAB. So now you see that, okay, I've found the intertwiner for this operator O. So, okay, okay, I'm still not proving this yet, but I'm almost there. I will keep the remark because that would be very important in a moment. So basically, from this intertwining relation, what we have is that this O of U naught alpha commute with T U naught alpha. But in the end, I really want UF. So how to find UF? Well, we know that UF is V multiplied by W, where W is just the G inverse Vj. And this is essentially just O squared with G squared. So this is a very simple manipulation that you can try, and then you will see that, okay, actually the Floquet evolution operator is just O squared multiplied by a translation to the right by 2 side. And since we know that we are studying some kind of a staggering transfer matrix, of course this commute with translation by 2 side if we have periodic boundary condition. So this is very easy to realize that the G squared just commute with, G squared just commute with the T, and this really implies that this UF commute with T for any spectral parameter value. And here it's perfect because we proved the theorem, so now it's really proven. And moreover, this remark applies, so basically I do not assume any of these nice properties of the R matrix, and you can still show that this Floquet dynamics is integrable. And basically this is a slightly bit of improvement of the previous work. For example, the first work that I'm aware of is the work by Destri de Vega, where in the 80s already, where they call this construction as so-called light cone beta ansatz. And also there's more recent work by Leonard Zadnik, who's here, and his collaborators, where they considered the explicit case for 6-vertex model, where this construction works. And then they managed to, okay, I don't exactly remember which year, but should be around there. They really proved the existence of the extensive amount of quantities, as well as it will contribute to like a non-trivial spin Jude weight, if I'm not mistaken. That's basically based on this observation that this time evolution operator is integrable. And in the case of, let's say, 6-vertex model, where the matrix, the R matrix is both of difference form and of permutation, basically from the picture of Destri de Vega, this circuits that we drew is essentially you can just think of it as some kind of a vertex model on a light cone. Sorry. So you can basically translate this picture into kind of a light cone coordinate, this kind of periodicity where, and this is actually nothing but related to the square of the transfer matrix that if you define like that way, because essentially this is equivalent to kind of this picture. And now we have this. So if you consider like a periodic boundary condition, and then you see that this operator is essentially this R check here. And if you just consider like two copies of the transfer matrix and you drag it straight, then you will recover this so-called light cone coordinate of the transfer matrix. This is a very nice, beautiful construction, and what we have contributed a little bit is just to see that this proof does not rely on any nice properties of the R matrix. We also even checked for very singular R matrices. Actually, it also doesn't depend on which representation. You can think of any representation, and with any higher rank underlying quantum groups that if you like for your R matrix, this construction always works because we don't assume anything. And with the remaining, let's say, maybe, 10 minutes, I hope, 10 to 15 minutes, I hope. And then I would like to just present to you some let's say, result to apply this, this nice construction. Namely, we consider the case of 6-vertex model. This, as I said, it's already been considered by Leonard and his collaborators. But the point is we use a little bit different R matrix, where basically it results in very different physics. The reason is because even though we just choose a gauge R matrix, since we're considering staggering, this gauge transformation actually depends on the gauge transformation actually depends on your spectral parameter. So in that case, you don't get the same model. Actually, you get a model with different transfer matrix, even though the structure is very similar. And the case that I consider is, let's see. So the example is that consider a R matrix that is related to the Templey-Lieb algebra. So it's 1 minus you can see that if I write like that, it means that it's of different. Where basically this eta is related to the so the exponential of the eta is so-called q, which is the underlying kind of UQSL2 structure, the Q deformation here, and my basically my R matrix. This so this part E it's related to the XXZ Hamiltonian in a way that is minus 1/2 sigma x a sigma x b. Okay, so this part is a bit boring, but just need to write it explicitly. So the interesting part, or in a sense, the difference between operation and the previous ones include this kind of magnetic field on boundary spins, such that this satisfy this nice Template-Lieb. Okay, let's first do EM is essentially EM, and this EM satisfies Template-Lieb of if you think of periodic boundary condition. So it's E beta and further away E it just commutes. So this is a representation of a fine Template-Lieb out. Which in the x-axis, where this is basically your anisotropy, is like your delta, which this is 2 delta. Okay, so if you choose this, okay, you might think, okay, so what's the problem? I mean, you can do everything there, but the only problem is that if you think about, let's say, the regime where delta is smaller than 1, the absolute value delta is smaller than 1, you would get that this Q is actually, in the sense that eta, sorry, it's not, it's complex, so eta is imaginary. And this will result basically this magnetic field to be imaginary. And moreover, since we know that the exponential of Template-Lieb is proportional to itself, it's like a projector, so actually, basically the R-check operator is literally the exponential of some Template-Lieb generator where this T naught is a function of alpha. So T naught is some function of alpha. Yes, so now basically what I showed you is that for this regime, if you think of this R-check operator is exponential of the Template-Lieb generator, and the Template-Lieb generator is not Hermitian because of the imaginary magnetic field, which means R-check is no longer unitary because it's exponential of some Hermitian, non-Hermitian operator. It's no longer unitary. So you might wonder, okay, but then in this case, your Floquet time evolution operator will be non-unitary as well. And this is actually a big trouble because if you really do quantum dynamics, you don't want to end up with, let's say, complex eigenvalues. But turns out that in our upcoming paper, we showed that this actually, this UF for this specific case, when eta is imaginary, it has this anti-unitary symmetry that basically is similar to the so-called PT symmetry that guarantees that the spectrum of, let's say, so now I'm just being a bit sketchy since I'm running out of time. So this UF, okay, let's say of T naught, is essentially just exponential of the Floquet Hamiltonian, where this Floquet Hamiltonian is no longer Hermitian, but it has some anti-unitary symmetry. And in that case, you can show that this Floquet Hamiltonian has either real eigenvalues or complex conjugate eigenvalues. And this implies that you might still end up with a real spectrum for your Floquet Hamiltonian. And that's exactly what happened is also very interesting that we found it first by numerically, is that there is a transition when you tune your parameter periodicity T naught. So for some T naught, you will end up with real eigenvalues of your Floquet Hamiltonian, and on the other one, you will have complex conjugate pairs. And in that case, in the case where you have complex conjugate pairs, this is in physics also called kind of anti-unitary symmetry breaking for the non-unitary, non-unitary Hamiltonian, and this already very interesting because it happens already for finite system size. So this is kind of some kind of phase transition that you do not need to take the thermodynamic limit, and that's what phenomenologically, that's what we have found. And moreover, for root of unity, so namely, if you consider q to the power of some integer is 1, there are some additional degeneracies for this Floquet time evolution operator. That is like in a sense very similar to what happened is that kind of when you tune your period, you see that your eigenvalues, which are supposed to be real for your Floquet Hamiltonian, they start to become degenerate. And when they get degenerate, it's like forming of Jordan blocks because we have non-unitary Hamiltonian, the eigenvectors might not be orthogonal. And then what happened is that when they kind of get to parallel to each other, then you form Jordan blocks. You have additional eigenvectors, and then when you start to tune it again, they split into the complex plane. So there's a bit of let's say relation to maybe to the non-unitary physics, especially non-Hermitian physics, especially maybe the relation to non-unitary CFTs or something like this, because for this model actually because in that case the transfer matrix is related to the so-called staggered 6-vertex model, where people find it to be some kind of lattice realization of non-unitary CFTs. So with that all being said, I'd like to conclude that so today I presented to you a very nice simple theorem that you can prove just using the integrability. And it implies lots of possibly very interesting applications that you can use all kind of R matrix. Maybe it will contain some different realization of some interesting dynamics, as well as some interesting symmetry, anti-unitary symmetry. There are still many things. For example, we found the integrable structure of the Floquet time evolution operator. We still haven't used it fully because, for example, we can use it to study the out of equilibrium physics such as quantum quench, or to study the inhomogeneous initial states such as to develop the, in which case, well, you don't have a differential equation for the hydrodynamics. Instead, you have a difference equation. And moreover, maybe there might be some other kind of interesting implications to extend this construction, because at the moment you only include the nearest neighbor interaction, but what happens if you have a Hamiltonian that has longer range interaction? So this has been looked at, so people call it a quantum cylinder automaton, but more detailed studies still need to be done. And with that all being said, thank you very much for your attention.
Thanks very much for the talk. Questions?
So is there experimental realization of this non-unitary UF but with this anti-unitary symmetry?
Yeah, that's a very interesting question. I think usually in experiments, the experimentalist would prefer to work with unitary gates because that's more natural from the experimental point of view. So I'm not aware of any realization of this kind of quantum gates, but of course there are some experiments that could work on non-unitary dynamics, but maybe more with continuous time, but not in this setup. But yeah, it's an interesting possibility.
Any further questions?
Shall I go? Okay. So you said that the conditions that you have real spectrum like depends on the symmetry, right? Which might present. And then you said that sometimes when you very T naught, which I presume is the same as spectral parameter, the symmetry is gone, or what's happening? It's
yeah, so it's always the symmetry is always there. You always commute with Floquet
yeah, okay.
Hamiltonian. But what happens is that it can be spontaneously broken. Yeah, so that's what happens. So you start with a spectrum, and then at some point it becomes complex conjugate pairs.
Okay, okay.
But before doing that, it get degenerate, and this is also very interesting in terms of, let's say, the non-unitary physics, where you have Jordan blocks in your Hamiltonian, more or less.
Okay. Thanks.
These degeneracies at roots of unities, are they related to semi-cyclicity of representations?
I think so. And numerically, what I observe is that so now I'm talking about the spectrum of the Floquet evolution operator, and they are located at roots of unity that are so in this case they are located at certain root of unity. Let's say we consider the case where Q is exponential of I pi L1 over L2, where L1, L2 are just coprimes. And your system size is L, and the eigenvalues of this UF, even though they are very degenerate anyway, but they are located at the root of unity exponential, let's see, I pi with some integer n over L2 multiplied by L over 2. So they are not necessarily occupy all the possible n, well n is some integer, but they always located as some root of unity that first depends on your original Q as well as on the system size somehow. So this is some numerical observation that we had, but we don't have a fully analytic understanding. But the symmetry somehow is there. So like the spectrum of this graph, it's very symmetric along some certain, it's distributed symmetrically on the unit circle. Because, at the transition,
The root of unity is of odd order, or it doesn't matter, the parity?
I think it doesn't matter,
Okay, thanks.
No problem.
Is there a way to directly find the eigenvalues and eigenvectors directly in the limit where you get these Jordan blocks, rather than studying the limit, but just directly at the point where these Jordan blocks exist?
Yes, a very good question. So because actually at that point it's a little bit difficult to study using integrability, because it corresponds to your spectral parameter goes to infinity. So maybe I would presume that in principle one should, in this case, one should just directly studying some, because we can construct, for example, from the transfer matrix, we can get the log derivative to get, let's say, some charge, where in this case, this charge should also Jordan blocks, and maybe directly on this level, maybe it's easier to study. And also the appearance of Jordan blocks is also very similar to the one in CFT in non-unitary CFTs. So maybe there are some connections, but I'm not aware of that at all.
Thank you. Any further questions? So if not, let's thank Yuan again for